Okay, it starts. Okay, now share my screen. Okay. So this is the radiation heat transfer equation. Okay, basically this is something called black body. Okay, if it's a black body, it's 100% efficiency on the radiation. Okay, so this is the maximum, basically. Okay, sigma, there's a name of this. Oh, by the way, A, obviously, you know what's A, right? It will be the surface area of the radiator. Okay, temperature. Okay, that's the surface temperature of that object. Okay, surface area, surface temperature. Sure, that's how you emit heat, right? Sigma is something called, it's a coefficient. Stefan Boltzmann constant. Okay, Stefan Boltzmann constant. So it's a constant, you know, it's also, well, people always know the radiation heat transfer is proportional to, of course, to the surface area, and it's proportional to temperature. And we'll find out it's proportional to the fourth order, power of 4 of the temperature, okay? But they are not exactly equal. It doesn't equal to A times TQ, right? So then we can have a coefficient in front of it, okay, to make them equal. So this is the Stefan Boltzmann constant. Yes, anybody want to talk something? Okay, so Stefan Boltzmann constant equals you can easily remember this. You know, this is when I was in college, so they teach heat transfer class, the professor actually asked us to memorize this constant. It's very easy. 5, 6, 7, 8. Okay. Now, did all of you remember this constant? 5, 6, 7, 8. Really not difficult to remember. Okay. Remember, a lot of stuff, you know, let's remember, they will be good. Watt meter square K to the power of 4. Okay, that's the unit for the Stefan Boltzmann constant. Okay, 5. I think in the textbook it says 5.669 times 10 to the negative 8. Basically, let's just do 5.67 times 10 to the negative 8. It's easier to memorize. 5, 6, 7, and 8. Okay.
Is K Kelvin?
Yeah, that's exactly what I want to continue to talk about. Very important. Thank you. Very important when you apply this equation, when you do this equation for calculation. It's very different comparing to conduction and convection. You have to use K. You have to convert your temperature into Kelvin, okay, in order for the calculation. Otherwise, we'll be totally wrong, okay? I think we have 19 of you in the class now. I want all of you, 19 of you remember this. When you apply radiation equation, it's Kelvin, it's not Celsius or not Fahrenheit, okay? But in those problems, homework problem, test problem, they always give you Celsius. Right? So if the problem has a convection and radiation and conduction all together, then they always give you Celsius. Okay, it's because in conduction convection they use Celsius or use Fahrenheit. It's very easy to make a mistake here. Okay, when you apply the conduction convection equation, you still use the Celsius, but when you reach to this term for the radiation, you change it to the Kelvin. Okay. Very important. Remember, okay, don't make a mistake on that. Okay, so this is the radiation from a black body, okay? How about you have two bodies or two surfaces? Okay, if you have two surfaces, let's say one surface is here, and then the other surface is here, okay? This is 300 degree C, this is a 100 degree C. Okay, so from each of the surface, well, you radiate the heat out, right? From 300 to 100. Okay, but the other surface also radiate heat out. So you receive some heat from the other surface. So you have to, if the net heat transfer rate will be equal to, well, if it's 100%, let's say if it's still 100%, right? Black body, both of them black body, no loss. Sigma T1Q minus T2. No, not Q, to the power of force. T1, T2. Okay, that's for each of surface. I think this is for the T1. At the T1 surface, what is the net radiation heat transfer? That's this. But how about in the T2? T2 surface, the net radiation will be negative. So it will be sigma T2 to the power of 4 minus T1 to the power of 4, depending on which surface you're looking at. Okay, so the positive heat transfer direction, heat flow has a direction, right? The positive direction is defined as the high temperature to low temperature. That's the positive heat flow direction. Okay, be careful. Okay, so this is the Q net on the T1 surface. Okay, the Q net on the T2 surface will be T2Q power 4 minus T1 power 4.
Does Q net not have surface area?
Oh yeah, it has surface area. I'm sorry, I missed it. Okay, here I said A1. So this is the T net for one surface. Okay. Well, I think if you use this equation, you can have to assume that A is the same. Otherwise, it should be, strictly speaking, it should be oh no, I'm sorry. I think this is still okay. You're talking about the surface one, so of course they use A1 for both of them. It's okay. I'm sorry, I said it wrong. Okay, so depend on which surface you're looking at. So the A is this. Okay, so I think I don't need this expansion because that's only the surface we're talking about. It's unnecessary, okay. Hey, I'm good. Now I'm good at the job board. Using erasers, nice. Okay. So this is a black body. What if it's not black body? Okay, non-black body. We have to introduce a something called emissivity, right? Let's see. It's called the emissivity. Okay. Epsilon. Is that epsilon? Is it called epsilon? The E, is that Greek letter or Roman letter? I'm really confused about the Greek letter and Roman letter. Okay. Help me if you can. To me, that's the letter E, right? I thought it's epsilon. Okay, but it's the emissivity. Okay, radiation emissivity. So basically this is it's a coefficient, it's efficiency, right? From 0 to 1. Okay, so you just added this coefficient instead of the equation, the net. Okay, okay. So what does epsilon equals 1 means? Hmm? And then what does epsilon equal to 0 means?
Like something to do with the efficiency?
Yeah, if it's equal to 1, that means black body. Okay, if it's 1, see, that equation will be similar to the previous equation. It'd be exactly same as the previous equation, right? So that's the black body. Okay, if it's 0, that means that surface totally it doesn't emit heat, radiation heat. Okay, so some color, I don't know. You probably can't reach exactly 0 and exactly 1. So, but anyway, it should be in between, just like efficiency. Okay, how effective, how efficient the surface radiate heat. Basically, that's what the emissivity means. Okay. Okay, I think I guess that's all the equations for the radiation. Not much, just adding one equations. So that usually the problem will be you have one surface enclosed into another environment with another temperature T2. So on that surface, what is the radiation heat transfer? Basically, that's what usually the problem is. Okay, so so let's look at a couple examples. So, what else? Let me see. Did I miss anything? These are the coefficient, right? Stefan Boltzmann. I want you to remember the Stefan Boltzmann constant. What is the value? Anybody?
Times 10 to the negative 8.
5.67 times 10 to the negative 8.
That's right. You have a good memory. You're smart. Okay. Let's look at the example. I think the example, start from the simple one. Okay. Example 1.5. Oh, that's so simple. All right. Too simple, basically. Okay. Doesn't matter. Let's do it.
Dr. Zhang.
Yeah.
Is figuring out if something a black body or not like something we're gonna have to do, or is the problem going to tell us?
Okay. Good question. Okay. Turn to the page if you have textbook. You don't need to. Okay. We're engineer. We're basically expert on reading tables. Okay. It's in Appendix A. Okay. On page 663. Okay. If you have book, you can take a look of the book. It listed, see, emissivity is nothing theory. Okay. It's kind of like a experimental physics. Okay. So everything emissivity is measured. Basically, it's from the experiment. Okay. And I don't think there's any theoretical background to derive the equation for emissivity. Okay, maybe there is, I don't know. Okay, but most of the time we use experiment to determine the emissivity. Okay, so on table A.10 on page 663, it listed all kinds of surfaces, aluminum, brass. In each surface, you always have different type of brass surface. For example, highly polished, hand rolled, a dome plate, chromium. Okay, all kinds. So for different type of surfaces, then you have copper, you have aluminum, you have gold, iron, lead. So all the surfaces, they gave you a temperature range. That means they tested only for this temperature range, the emissivity. Okay. So for example, for the highly polished brass, for the temperature between 476 to 674 Fahrenheit, And the emissivity is between 0.028 to 0.031.
What page was this again?
Okay, page 663. You asked for the page number, right? Yeah. And see, it give you a temperature range, and it give you also a emissivity range in this temperature range. So you need to make some decision, make some calculation, maybe linear interpolation or something like that. For example, your temperature is 500 degrees. So probably I would say my emissivity should be 0.029 for this polished brass surface, okay? I'm sure that there are more detailed tables for each different, for all kinds of different surfaces. But I think that here in the textbook, this is the only table I find from page 663 to page 664. Okay, pretty long table. It listed, I think, many of the different surface, different material. Okay, and the different type of surface in each material, okay? And many of them has a temperature range and therefore has a emissivity range. So you probably need to do some interpolation, okay, for a particular problem. Does that make sense? Okay, good. Barely has a black body, close to black body, I think. Most of them, the emissivity is kind of less than 0.5, okay? I have several of them. Nickel oxide surface, it's like a 0.59 to 0.86. That's one of the higher one. And nickel alloys, nickel wire oxidized, this is almost black body, 0.95 to 0.98, okay? So yeah, that's a table you can use for the actually calculation, okay? Good question, yeah. So let's come back to example 1.5. Oh, that's easy, let's read it. Okay, let's say two infinitely black plate. Okay, that's easy, we don't need the emissivity. It's black plate, okay? So two plates, T1 is 800 degree. This is example 1.5, okay? T2 is what? 300 degree, okay? Celsius, okay? Exchange heat by radiation, calculate the heat transfer per unit area, okay? I guess that's the equation we're gonna pick is Q equals to sigma times area. The area, actually you can divide it to the left-hand side, right? So T1Q minus T2, oh no, I keep saying Q. It's power 4, okay? Okay, so it asks you heat transfer per unit area. So it's Q divided by A. It's what we want to calculate, right? Let me move this Q over A to here. Q over A, that's exactly what you want to calculate. So equals to, okay, now you need to write down your Stefan Boltzmann constant. -8, okay? Unit is what? Watt meter square K force. Okay, then temperature. Again, don't put 800 here. Don't put 300 here. It give you 800 Celsius. What is Kelvin for 800 Celsius? 273, right? Is that right? Is that 273 is 0 Celsius?
73.15, something like that.
Yeah. Let's get rid of a 0.15. Come on. Too difficult in calculation. So 273 plus 800, 1073 to the power of Q. So radiation problem, you really need your calculator. A lot of calculation. By hand is probably pretty difficult, okay? 300 degrees. So 300 plus 273, 573 to the power of 4. Okay, then that's just calculation. Kelvin and the Kelvin. Okay, that's why the Stefan-Boltzmann coefficient is, the unit is K to the power of 4 in the denominator, right? So you K to the power of 4 can cancel. Then the unit become watt per meter square for Q divided by A, okay? So the result is what? 69030 watt per meter square. I don't like the textbook always keep directly putting down kilowatt. From this calculation, there's no way you can get the kilowatt directly. The calculation from the unit, you know, it should be watt per meter square, okay? Sometimes we'll make a mistake by doing the kilowatt too much. At the end, you want to convert to kilowatt, go ahead, okay? But during the calculation, be careful. So it's equivalent to 21.884 BTU per hour. Is that 21,000 or 21 point? But doesn't matter. You can convert. Okay, BTU per hour per feet square. Again, I think I mentioned this before. Watt. You know the unit of watt, right? Watt is per ton. Okay, just like a BTU per hour. Okay, be careful because some of the homework problems, although I didn't assign, some of the homework problems we ask you what is the heat transfer per hour. Okay, it's the same thing as watt, right? Okay. Okay, this is the simple one. I don't think anybody has a question, right? For this one is simple. Just be careful when doing the calculation, temperature, use Kelvin. That's it, I guess. That's okay. The next problem is maybe a little bit more complicated. Let's see the last example, example 1.6. Okay, okay, it looks like a more applied problem. A horizontal steel pipe having a diameter of 5 centimeters is maintained at temperature 50 degrees Celsius in a large room. Okay, so you have a pipe. Okay. 5 centimeter diameter. The temperature of the pipe is 50 degrees Celsius. Okay, the room temperature, T infinite. I'll keep using T infinite, so that means it doesn't matter is a room or air or whatever, it's just ambient, okay? 20 degrees Celsius, okay? See, this is how I solve problem. I always when I read the problem, I try to draw some diagram, okay? Then after I read the problem, I have the diagram, then maybe it's easier to do, okay? Easier to solve it. The surface emissivity of the steel may be taken as 0.8. So your emissivity is 0.8. Again, emissivity has no unit. It's a coefficient. It's a efficiency, basically, okay? Using the data of table 1.3, calculate the total heat loss by the pipe per unit length. Total loss. Table 1.3. What is table 1.3? I think that's the convection heat transfer coefficient, right? Oh yes, table 1.3. If you turn to the page 11 for table 1.3, I think it gives you the convection heat transfer coefficient of this 5 centimeter. It's down there. Horizontal cylinder, 5 centimeter diameter in air. Okay, and free convection delta T 30 degrees. Oh, that's exactly this problem. Free convection. Okay, they didn't say there's a flow around it, right? So basically it's a free convection. So the convection heat transfer coefficient of this, I think in the table 1.3, it says 6.5 watt per meter square C, okay? So obviously from this problem, from the problem statement, you know, there are two heat transfer mechanism here, okay? Well, it's luckily it's not three, okay? It's only two. So it's the convection and the radiation you have to consider from the surface of the hot pipe to the environment, okay? So Q equals, you know, before you even, you know, whatever calculation or input on any numbers, write down the equation, okay? And or maybe you can write down a step like this. Even write a equation like this. Just tell me, I understand that this problem has two mechanisms, convection and the radiation. I give point to it, maybe not much, but I give point for you. Just tell me, you know the right direction. How about that? When you do test, think about how the teacher will grade. Okay, this is my trick, okay? I did well in my college on the tests. I don't remember much of the knowledge, you know, I'm terrible. But I did good on tests most of the time because I know how to do tests well, okay? At that time, I mean, when I was 20s, my goal is not to learn the knowledge, and my goal is just pass the test and get a job, okay? Just like you guys now. Okay, but that's okay. Well, it's capable of doing a test, pass a test. It's very important because your job eventually is a test. Every project you have, basically you have a deadline and then you have to pass it basically. So when I was in the test, I would think about what teacher think, what teacher, how him to grade. You know, how is the teacher going to grade? Because teacher has the solution manual down there. Okay, there's the steps in there. Okay, if I was a teacher, I would say I check every step. If I have it, then I give point to the student. If I, you know, cannot clearly see this, I feel terrible. I feel mad. Okay, so you don't want to, you know, your test made me feel mad, right? so write all the steps necessary. Then it will be very neat paper. Okay, if it's never needed, including all the steps, it's very difficult to get the bad score. Okay. Because whatever you wrote, you will get some points. Okay, so this is the total conduction convection. Okay, so let's see can we expand these two terms in the right-hand side of the equation. Okay, convection, I think it's kind of easy. H times the area times T surface minus T infinite. T surface, I put the S here. Okay, right? No problem, right? Plus the radiation. Radiation, do you remember? It's not a black body, right? It is, but it gives you the emissivity. So emissivity times the Stefan-Boltzmann constant, 5.67 times -8, okay, times T surface to the power of 4 minus T infinite to the power of 4. Okay, you see, I write on this, it bury a seed for making mistake. Now it seems like TS, T infinite happened 2 times. If you're too hurried, then you just put in the temperature in Celsius in both parts. Then it's wrong. Okay, be careful. You can put the Celsius delta T there. You use the Celsius, but for the radiation part, put the K, Kelvin. Okay. Yes, what? Okay. So I guess. Oh,
What about the area?
Yeah. Yes. Okay. Now let's come back to the question. It says it doesn't give me the total length. So I cannot calculate the area of the pipe, right? Outside the surface area of the pipe. But they asked me the heat loss per unit length. So it's per the length of the pipe. So it's divided by the length. So Q divided by the length, that's what we want to calculate. So in that sense, the surface area is what? It's just the circumference of the pipe times the length. So it can be, length can be moved to the left-hand side. So it's okay, right? So equals H is 6.5 watt meter squared C. Now area become what? Pi d, right? Become the circumference of the perimeter, circumference of the pipe. Pi times diameter. Okay, diameter is 5 centimeter. Very careful. 0.05 meter. Okay, be careful. Again, always I want to remind you. Okay, the temperature difference, Ts minus T infinite, 30 degree Celsius. Okay, so it's okay. So you should be able to calculate the convection. Okay, I think I have everything in here. Okay, in the right-hand side. So I should be able to directly calculate it. So epsilon is 0.8. Stefan Boltzmann. Then convert to Kelvin. 50. 50 is 323. 20 is 293 K. Okay. Is that right?
Your area.
Oh, I missed that again. Pi d here, the same pi times 0.05. Yeah, you guys probably can see area than me. I'm too close to the whiteboard. I'm writing it. I missed something. Sometimes I didn't notice. Good. Thank you. I have everything on the right-hand side. Okay, so I think this thing can be calculated. Then everything just key in the calculator. Is 25.04 watt per meter. Okay, that's per length, right? This is the power heat transfer loss per length of the.
I think that's just for the radiation, the 25.04.
Oh, okay. Oh, okay. I look at the wrong place. Okay, thank you. 55. Yeah, it's on the next page. So adding them together. Per meter. Okay. They're good. So now you have I assigned several new problems. If you look going to Moodle, you see I assigned 4 more problems for chapter 1. That's it. All problems. That's all the homework for chapter 1. Okay. So now you learned basically you learned all 3 mechanisms: conduction, convection, radiation. So the key of solving this problem, you could read the problem as long statements or whatever. Seems like a headache, But hey, just try to divide and conquer. You can separate this whole picture into conduction, convection, and radiation. Okay, look at them separately, and then you should be able to solve those problems. Okay, and each conduction, convection, radiation has separate equations. Then just list the equations, see which letter is your unknown, which letter you don't know. Then one equation you can find out one unknown, right? So, but I think the key is to separate into the separate mechanisms for a comprehensive problem. Okay, that's it. That's it for chapter 1. Is that good? Now you have a feel of the heat transfer, right? It's not too bad, huh? okay? Energy, and one form of energy is heat. Heat always goes from the high temperature to low temperature. That's about it. And they have different separate mechanisms: conduction, convection, radiation. Okay. So the second chapter, later chapter, we're gonna focus on each of the mechanism. For example, conduction. We're gonna look into more details, more difficult problems, more applications. Okay, in conduction, convection, and the radiation. Okay. So I guess that's it. It's Friday. I'll let you go early, 9 minutes early. Any questions?
Dr. Zhang,
Yes.
I had a question about 1.7 again.
1.7. Okay.
Yes, sir.
Oh, okay. We talked about that problem last time. Yeah. What's your question?
Whenever I was setting it up, I got my conduction rate and I got my convection rate, and I got the conduction equals convection plus radiation equation. I don't know how to get my Q and L basically on the same side.
No, your heat going out of the material, okay, will be equals to the convection plus radiation, right? Do we have a radiation in that problem?
It was 0 on that problem, but.
So it's a convection only, right? So.
It's not conduction because of the insulation?
Yeah, insulation part is the conduction. When the conduction goes through the insulation, will be equal to the convection going out of the insulation. That's the equation you should start from. I think the difficult part for that problem is the convection, because it's a cylindrical coordinate. Your insulation, it's like a ring. We had exactly that problem in the class, example problem for the cylindrical coordinate, remember? That's exactly that conduction. So, but you have to equal the conduction Q equal to the convection Q. Okay, based on that equation, you should be able to find the one unknowns, right?
Gotcha.
Because you don't have the temperature on the surface. I think this is a hint for you.
Right. I had got a value for each one. I just don't know what to do with it.
You shouldn't get the value of each one. They are the same. Okay. Before you can figure out the surface temperature, you shouldn't be able to find any Q.
Okay. Gotcha.
Okay. Your difficult part is the surface temperature. You need to know the outside surface temperature when exposed to the air.
Okay.
Which is not given, right, for this problem.
Right.
So that's how you use that equation Q conduction equal to Q convection to figure out that T surface.
Gotcha.
Right. That's why I said this is a difficult problem, because that conduction part of the calculation a little little because it's cylindrical coordinate.
Okay.
Yeah. Okay.
Gotcha.
Okay. Good. Any other questions? Good. Okay, so have a nice weekend. Okay, happy Friday. See you next Monday.
Bye.